A long time ago, there lived a little man named Blue. One day, when Blue was walking around in the big city, a flyer caught his attention. The king is holding a sailboat race in 2 weeks' time, and the winner will be given enough gold to live happily ever after. But there was a problem. Blue doesn't know how to build a sailboat. So he thought to himself,
If I'm going to win this competition, I'll have to get some help.
Blue decided to go to the University College of La La Land to look for help. There he found Professor Reed, who happened to be a professor from the Mechanical Engineering department. Blue knew that Professor Reed will be able to help him build the sailboat.
Good day, sir. I have to build a sailboat. Can you help me, please?
Professor Reed, known for his intelligence and kindness, naturally said yes. So for the next few days, Professor Reed focused on helping Blue fulfill his dreams by designing a sailboat. Reed brought Blue to a classroom and started explaining the concept of drag and how it will affect the speed of the boat.
The most important thing to a successful sailboat is the concept of drag. The sailboat uses the wind energy to generate a drag force, pushing the sailboat ahead. Let me explain more about drag. Total drag is made up from form drag and skin friction drag. Form drag depends on the shape of the body, where the cross-sectional area and streamlined shapes are the main factors. Maybe you should experience this for yourself. The orange parachute has a bigger cross-sectional area, allowing it to catch more wind and therefore generate a greater drag, or wind resistance force, which is why it is hence slower than the smaller parachute.
Conversely, the size of the mainsail will affect the speed of the sailboat. A big mainsail will result in a greater drag force due to the wind, which will push the boat along with it. This is useful drag.
While we're on the topic of form drag, the shape of the boat will affect the drag it generates. The shape of the boat, which comprises of the nose, body and tail, can determine if the boat is streamlined or bluff. Let me show you an example. If we drop two solid objects into a liquid, the more streamlined object will go down faster. So, you should keep this in mind when building your sailboat.
In other words, a sailboat with a more streamlined shape generates less unwanted drag, and hence travels faster in the fluid.
Moving on to skin friction drag, which is dependent on the viscosity of the fluid. The viscosity or thickness of the fluid is a main component of the skin friction drag. Let us see an example. A more viscous fluid, in this case a body wash, would generate more drag compared to the water. Hence, even when we put two identical objects into the two different fluids, one would go down slower than the other.
I kind of get it now, but is there a way to calculate drag force?
Ah yes, let me introduce you to the drag formula. F equals to half rho u square CD times A, where F is the drag force, rho is the density of the fluid, u is the relative velocity, A is the surface area, and CD is the drag coefficient.
So how do these factors affect the drag force?
It is important to note that all of the factors are proportional to the drag force. This means that when any of these factors increase, the drag force will also increase. As we are looking for the sailboat example, the factor's density and the velocity will not be as important as the other factors. But the area factor, like in our parachute experience, is classified as form drag. As you may remember, I mentioned the shape factor and the skin friction drag. These are classified under the drag coefficient, and the values can be found experimentally. We saw that the higher the viscosity, the higher the drag coefficient. Conversely, the more streamlined the shape, the lower the drag coefficient. In your case, you should concentrate on the boat shape and the area of the sail to build the boat.
Okay, but is there a way for me to measure this drag?
Ah yes, I'm sure you know what Hooke's law is, right?
Yes, it's F equals to kx, where k is the spring constant and x is the extension.
Yes, so you should know that the longer the extension of the spring, the larger the drag force.
Yes.
Good. So in order to measure drag, we can use a spring like this.
Oh, I see. I get it now. This concept is so cool.
Yes, Blue. Not only is it cool, this concept affects our daily lives.
But how?
Let's think about it. Generally, we know that objects that fall will keep getting faster because of gravity. But eventually, they will reach a maximum velocity, known as terminal velocity. This maximum velocity is reached due to the existence of drag force. Let us think about our parachute experience. With the drag formula, we can assume that the density of the fluid is the same as they are both air. We can also assume that both people had the same weight, and the only difference between the two parachutes are the surface area. It is important to know that the relative velocity will change constantly until terminal velocity is reached. This is when the weight of the person equals to the drag force. So, because the drag force generated is greater for the larger chute will reach terminal velocity in a lesser time compared to the smaller chute. This also means that the value of the velocity is smaller, which means that the man with the bigger chute will descend slower. Get it?
Wow, I'm truly amazed, Professor Red.
Also, on the larger scale, drag can affect how planes fly, how athletes choose their clothes, and why fishes swim faster than humans.
Over the coffee table, Professor Red told Blue more about how drag affects his job as a mechanical engineer.
As a mechanical engineer, it is important that we understand how the concept of drag works. In the larger scale of things, we can calculate the various types of drag generated. This can be foam drag, skin friction drag, parasitic drag, induced drag, and more which you may get to know.
But what will you do with this?
Patience, young Padawan. Understanding this drag can help us improve products, like aerodynamic design to reduce drag, and help objects like bullet trains, cars, or rockets move faster. We can also figure out the optimal shapes to generate drag, to build better parachutes or sails. Understanding the magnitude of the drag force can also ensure that our structures or equipments do not collapse or fail over time. These are just some of the implications of drag, which we as mechanical engineers need to know. And for you, of course, to build a better sailboat.
Thanks very much, Professor Red. I think now I have a much better idea on how to build a sailboat.
No problem, Blue. You probably should go and start building the sailboat before you run out of time. Good luck with your race.
Blue went on with his newfound knowledge to build a sailboat. Blue won the goal and lived happily ever after.